Welcome everybody to episode number 5 of my lecture series for Chemistry 12. Don't forget I'm following specifically the BC curriculum, so this is designed for grade 12 students in Chemistry 12 in the province of BC. Of course, chemistry is chemistry, so it applies all over the place, but if it's not following exactly what you do in your province or in your jurisdiction, that's because I'm tailoring it to students in BC. So today we're doing solutions of strong acids and calculations related to pH, okay, of those solutions. Because I haven't done it yet, before we actually get into how you do those calculations, you have to first understand what the difference between a strong and a weak substance is. So there are strong acids, there are weak acids, there are strong bases, there are weak bases. So what does that term strong and weak actually mean? And it has to do with a concept known as percent ionization. So I need to do all that definition stuff before you can get into any of the calculation stuff. To be honest, the calculation stuff is actually pretty straightforward. Won't take very long at all. That's pretty easy. But you have to understand the difference between the two of them. The first thing I want to say about the definitions of strong versus weak, it has nothing to do with pH. Absolutely nothing. Don't say, well, this solution has a pH of 1, therefore it's strong. It doesn't work that way. The strength of an acid and the strength of a base doesn't have to do with the pH of the resulting solution that it makes. It has to do with how well that acid or that base chemically reacts when you put it into water. How well it either donates an H if it's an acid or picks up an H if it's a base. So that's kind of the critical component of it. So we've got 3 things to do today. One, we've got defining strong versus weak and how percent ionization kind of fits into that. What does it mean? Do some logical things behind that. Then identifying what the strong acids are. So like, how do you know you've got one of the strong acids that we're even talking about? And then once you kind of get all that behind you, then you can go into the calculations, and then it's pretty straightforward. Next week we'll go into, or sorry, not next week, next class we're going to go into how do you do it when it's a weak acid. So a slightly different method to doing the calculation stuff. So let's get right into it. So the very first thing that we're going to do is categorization of different chemicals. And you can see here over my shoulder that I've already written this down on the board. So kind of just generic chemicals in solution. So you take anything and throw it into water and it dissolves into the water. Does that chemical, when you put it into water, and again, it's got to be in water that we're talking about here. So if you put it into water, does it act as an acid? Does it act as a base? Or does it do nothing and just floats around and the solution ends up being neutral? So I've got my 3 kind of categories that are up here: acid, neutral, and base. The neutral things we deal with later. Okay, you have to have a little bit better understanding of Ks, Kbs, what makes an acid, what makes a base, before you can actually backtrack and look at, well, this thing's neutral. So we do that afterwards. So let's take a look at these. You'll notice that I've got the acids and the bases categorized the same way. There's weak or there's strong. They do not have to do with whether they produce high or low pHs. It has nothing to do with that. So you'll see that in my categorization, the strong acid and the strong base, they've got that green line kind of pointing to the same thing, which means the word strong is a descriptor of the chemical and what it does, regardless of whether it's acid or base, regardless of whether it makes the pH above 7 or below 7, doesn't matter. The green line is pointing to 100% ionization. 100%, mean all of it. We'll get into that in just a sec. The red line that I've got here, so the weak acid and the weak base are pointing to the same thing. They're pointing to the less than 100% ionization. So to define or categorize strong versus weak substances, it has to do with whether or not they put them into water and they react 100%. React meaning ionize, because that's what acids and bases do. They ionize. So you put them into water. Do they do it 100% or they do it not 100%? And if it's not 100%, it's considered weak. You will find that those things that don't do it super well, the weak ones that we're going to categorize, they do it really not well. So it's usually far below 100%. So it's not like, oh boy, what do I do with the one that's 98%? You typically won't have that one. It's going to be, you'll see that in the chemistry world that they tend to be really good or they tend not to be super good. So we've got that basic categorization, okay, strong versus weak. Now, in order to kind of get what it really means, you need to understand the definition of percent ionization. So what is percent ionization? And once you kind of get that concept, then you can categorize. Yes, it goes 100%, or no, it's less than 100%. And there's chemistry reasons why, and equilibrium and stuff, which we'll get into as well. Okay, so let's talk percent ionization. So take a snapshot of that. So I'm going to specifically talk about acids. The concept will come up again when we talk about bases, but what I plan on doing is, and what I typically do is I go into acids. I kind of deal with strong ones and weak ones, and we get really good at the acids and what did they do and their pHs and strong, weak, percent ionization, all that kind of stuff. And then we switch over to the bases. There's some kind of tricky things that are related to the base. So I like to kind of cover all things related to acids first. So I'm going to stick with percent ionization of an acid. So percent ionization of an acid, there's a little formula, okay? So sometimes the math helps people visualize what's going on. So percent ionization could be represented in a little mathematical formula. So the percent ionization of an acid equals, and this is, if you think of the chemical reaction of taking an acid and putting it into water, and what does it do? It donates an H to the water. So percent ionization has to do with how well that reaction happens, how well the acid molecules download an H onto water molecules. And so to quantify that, you would figure out, well, okay, so what percentage of those acid molecules that you throw into the water, what percentage of them actually do the reaction? And that's what percent ionization actually is. So if here is our reaction, here's our generic, and if you remember, I use the little HA to signify a generic acid. Doesn't matter which one, it's any acid. There's our acid in water. Goes to hydronium and whatever the anion was of the acid. So it's called its conjugate base, if you recall the terminology. So percent ionization, this is the reaction. So percent ionization is really saying, it's a quantifying of how many of these molecules turn into the products. And so the mathematical formula shows that. And it is how many of those things produced. Okay, so how many hydronium ions get produced for when compared to the original acid concentration that you threw in. Now, it doesn't necessarily have to be in concentration. It could just be number of molecules as well, moles, if you wanted to. Of course, it's a percentage. So if you do this fraction, it's going to come out to either 1 or less than 1, like a decimal. So it's somewhere between 0 and 1. So to turn it into a percentage, obviously, mathematically, you're going to have to move the decimal 2 places to the right to make it into a percentage. So that's why it's times 100. So percent ionization is how many of these turned into those. So I just kind of keep this relatively simple here. So I'm going to write down Okay, you've probably seen one of these before. You've done the equilibrium unit, you've done the solubility unit, so you've probably seen a chart that looks like this. If you haven't, not quite sure what's been going on, but the words that are used might be slightly different. In my class, I use the words initial, I use the words reaction, and then typically I use the words equilibrium. I'm using the word end here just to signify, okay, at the end for our calculation, just for me to demonstrate this point. So let's pretend I take kind of weird, just kind of random number. 847 molecules of HA, and I dump them into water. Completely random number. That's obviously a very small number, but 847. And I throw them into water. Okay, so what else have I got initially? Well, the number of water molecules, I'm dumping HAs into a beaker of water, so there's a gazillion water molecules in there. So, and their concentration isn't going to change anyway. So you've kind of gotten in the, you should start getting into the habit of anything that's in liquid form, generally speaking. You're kind of crossing it out because it's not changing in concentration, so it's never involved in the equilibrium calculations that you've been doing. So we get rid of it. These two initial values, I'm going to put zeros, meaning you don't have any yet. So you dump the HAs into the water. If you could slow down time, like super, super slow, and you take HAs and you throw them in, the very first thing they do is they form a molecular solution. Before they bumped into any water molecules, like if you could slow down time that much, before they bump in and start reacting, they start to spread out individually because they're polar molecules. So they've dissolved first, then they bump into water molecules. Of course, it gets messier than that. If it was a real situation, it gets a little messier than that. But because they haven't yet reacted, you have 0 and 0. You haven't made the products yet. Now, some of you might be saying, wait a minute, because you're dumping them into water, and water didn't have 0 hydroniums, and if you're thinking that, you'd be right. There is hydronium in water. If there was a beaker of water before you threw HA into there, yeah, it's at equilibrium. It's at 25 degrees. If it's at 25 degrees, it has 1 times 10 to the negative 7 molar of hydronium. Remember, we've been using that number a little bit here. So that isn't truly 0, but that number is really small compared to what the acid is going to make. And so because it's really small, it's insignificant relative to how much the HA is going to make. It's a little bit of kind of theoretical mathematical logic there. So for all intents and purposes, the hydronium started at 0. Okay, and just kind of think of it that way. So to demonstrate the concept of percent ionization, that if you think about it, if we start with 847, if every single one of those molecules, every single one, all 847 of them, chemically reacted, every single one, how many HAs would be finished? Or would we end up with? We'd end up with, well, 0, none of them. They'd all disappear. They've all chemically reacted. Using your basic stoichiometry, how many hydroniums do you get? Well, it's in a 1-to-1 ratio with the HA, so this would have gone up 847. You would have also have made 847 A minuses. And so at the end of the day, you would have ended up with 847 and 847. Well, if you look at the formula that I've got up there, if you take the number of hydroniums that get produced at the end, compared to how many HAs you started with, not with how many you ended up with. You started with 847. They all turned into hydronium. So that fraction would be 847 over 847. Well, that's 1. 1 times 100 is 100%. So if every acid molecule turns into hydronium, that is a 100% ionization. It turned from a neutral acid molecule into 2 ions. And so therefore, you've got 100% ionization. Obviously then, well, what if What if? A lot of what if. Actually, before I do that, let me point something out to you. That looks very similar to what you do in Chemistry 11. In Chemistry 11, and you probably were shown this when you were doing equilibrium way back when in Chem 12, that Chem 11, every single calculation you did in Chemistry 11, we assumed 100%. You always do that. You assume 100% so that one of the reactants disappears, and we call it the limiting reactant. And the stoichiometry becomes really simple, right? Then you can just use basic ratios, mole ratios of the coefficients, and you can determine how much you've got at the end. Chem 11 was the simplified version, and Chem 12, it doesn't work out quite that way. Not all things are going to go 100%. The only ones that do are those that we would consider strong. Okay, certainly in the acid-base unit, strong things do what Chem 11 would do. They go 100%. One thing runs out, you end up with equal number of products as you had of the reactants. So, but this is Chem 12. So in Chem 12, it's not always that simple. And so, what if they don't all go? What if, I don't know, say the HA, and let me give you a little bit of a background, a little bit of a story to kind of get this. Let's pretend the HA molecule itself. The A and the H are covalently bonded, and they're really strongly bonded together. They like each other. They're not superpolar. The H is really stuck onto that A, whatever that A is. It's stuck on there really, really well, and the A doesn't want to give up the H. Well, when it bumps into a water molecule, it's not necessarily going to transfer the H just because it bumped into it. It's going to be harder then to transfer that H. And because it's harder to transfer that H, not as many molecules are going to do it. Therefore, what if HA happened to be something that didn't want to get rid of its H? It still does, but not super easily. Let's say of the 847, only, small number, 3 wanted to do it. Well, if 3 wanted to do it, then 3 reacted. That means you'd make 3, 3, 844. That is going to give us a percent ionization way less than 100%. It's going to end up being 3, that number right there. There's that guy. 3. Was right up there. We're 847. 3 out of 847 turned into hydronium. Well, you do that math, and you're talking about a small percentage. It's about 1 out of 300. Well, that's pretty darn small. Okay, so you're talking about, what is that? That 0.3% ionization. So that's way less than 100%. This thing is a weak acid. Weak meaning it doesn't want to give up its H, and so it doesn't go 100%. If you've got an acid that, HA, you've got an acid that the A isn't holding on to the H very strongly, and that's typically what happens when you've got really polar molecules. And the H is barely hanging on for dear life. If it bumps into a water molecule, that H gets delivered really easily. And that's what you get if you've got a strong acid, is the A is not bound to the hydrogen very strongly, and so it falls off really easily. And so literally 100% of the molecules get rid of their H, and it's strong. So strong and weak kind of have to do with how well that H is stuck onto the A, and therefore how easily and what percent get transferred over to a water molecule. 100% of them, strong. Less than 100% of them, weak. Now here's an interesting scenario. Okay, I'm going to give you kind of a weirder little scenario. Oops, I don't want to erase that. Okay, hopefully this is not going to be too small for you to see. What if I throw in 1 million HAs? A million. And 999,999 of them get rid of their H. How many are left? 1. How many hydroniums do I make? Well, that goes up. That's a lot of 9s. Okay, so you start with 1,000,000 HAs. 999,999 of them unload their H onto water molecules. You end up with 999,999 hydroniums. 1 HA is left over. The percent would be 999,999 divided by 1,000,000, which is 99.99999%. That's not 100%. Now, in the chemistry world, we're talking about numbers, and I mean, even 1,000,000 is a small number. Can you assume this is 100%? Like, could you even, from a practical perspective, could you even measure 1 HA left over? Could you tell the difference using whatever piece of equipment you have? Could you tell the difference between 999,999 versus 1,000,000? Probably not. And these are small numbers relative to the actual numbers we're dealing with. I mean, a mole is 6 times 10 to the 23rd. So, what does 100% actually mean? And the definition of a strong acid means, for all intents and purposes, it goes 100%. Not necessarily exactly every single molecule. Because what I want you to remember is that regardless of what chemical you're talking about, and I've kind of messed up my equation here. Regardless of whatever chemical you're talking about, they can always turn around and go back the other way. So even if you've got a really strong acid, it unloads its H really, really well, it can still turn around and go back the other way. What strong acids do is that they get rid of their H so easy, and it's so hard to put the H back onto the A-, that they are, for all intents and purposes, 100% to the product side. For all intents and purposes. The reality is they're not, but for all intents and purposes, they are. So for our purpose of calculation, we make the assumption that for a strong acid, that it goes 100%. And so we use a single arrow to indicate that it goes 100%. Now, why? Well, even if there is the odd molecule of a strong acid that doesn't turn into the hydronium, it is so insignificant relative to the number that do, that mathematically we can just ignore it, okay? Because we can't even measure it. We're just not precise enough to be able to measure that molecule. So we might as well just pretend that it did go 100% from a mathematical perspective, and you'll see it makes the math way easier. So which acids actually go and do this? There's an actual limited number of acids that have this ability to do it. In my class, people have to have them memorized. Now, it's not super hard because I provide a data table, and all chemistry people do. They provide a data table where it's called the Ka table. We just refer to it as the Ka table. It's a giant list of acids, and it's for those of you who are in the province of BC, we hand out a data booklet. It goes with the provincial exam, and I guess not everybody does. Some people use their own Ka table. I've kept going with the data table that we used to give for the provincial exam, which they haven't really done in about 10 years, but I still use the same data table. Hasn't really changed very much. And it looks like this. And it's in your data booklet if you're a teacher. If you are in the province of BC. And they use the old provincial exam data booklet. It's on page 6 of the old data booklet. And you can see that up at the top of that data booklet, there are 6 acids that are there, that they have their names, they have their formulas, they're shaded gray. And then if you look at the arrow, it's a one-directional arrow towards the products. And then over underneath the title KA, it says very large. Now what that means is those 6 acids, they go so much into the products that you can assume that, imagine if you did a KA for that last one that I did, you'd have 999,999 times 900,999 over 1. Well, that's a huge number. And so because it goes so far to the products, those Ka values, like the equilibrium constant for the acid, is a massive number. And so strong acids, they go 100%. There are 6 of them. They're in the data booklet. They're usually labeled. They have a one-directional arrow towards the products. And you have to know this because you deal with them mathematically slightly different. So what are the strong acids? And just, you should know them kind of off the top of your head. So I'm going to list them here. I'm just going to put them in a list across the board. So the first one is perchloric, which is HClO4. That's perchloric. Then you've got hydrobromic, hydroiodic, hydrochloric, nitric, HNO3, not HNO2, nitric, and then the last one is sulfuric, and it happens to have 2 H's, and it's kind of an interesting one because it has 2 H's, and we'll get to that one later on. There'll be another lecture on polyproducts. So these are the 6 acids that get rid of their first hydrogen. If they've got more than one, they get rid of their first hydrogen 100%. You throw them in the water. Every single molecule gets rid of its H onto water molecules and makes hydronium. So if this is the case, like, memorize the list. I mean, it's on your data table. They're right there. It's those guys right there. So those 6 will go 100%. So how do you deal with this? How do you deal with this mathematically? Okay, so those 6, snapshot, cool. They all have a 100% ionization. You can use that to your advantage. Knowing that they go 100%, if I tell you something about the initial concentration of an acid, and it happens to be one of the 6 strong ones, you know that it has ionized 100%. So I'll give you an example. So here's a question. What is the pH of a 0.080 molar HNO3 solution at 25 degrees Celsius. And I'm just always going to put at 25 degrees Celsius to kind of get you in that habit of thinking 25 degrees Celsius. So what is the pH of that solution? So what do you know about these acids? Well, okay, so the acid, how did you make that solution in the first place? You took some HNO3, you threw it into some water. You threw it into some water in such a way that the concentration ended up being 0.080 molar of the HNO3, right? So that's like think of a Chem 11 question. You take this amount of HNO3, dump it in water, what's its concentration? Well, if the answer came out to 0.080, that's what we have. So you've got this bottle of HNO3, it's labeled 0.080 molar, it's at 25 degrees. What's the pH of that solution? So what you need to know to get a pH is you need to know the hydronium, because mathematically, hydronium negative log of that concentration is going to give you pH. So that's kind of your strategy of how you're going to do that. You need to take the concentration of the acid to get the concentration of the hydronium to get the pH. So from a strategy perspective, you're going concentration of the HNO3 initially is going to give you the concentration of that. I'm going to use a little EQ even though it's end, final. And then you're going to get the pH. Kind of like you're mapping out a little strategy of how you're going to do it. What is the theory behind what you're going to do? Well, what you're going to do is because HNO3, you go, oh, okay, that's one of those 6 strong acids, which means it ionizes 100%. When something ionizes 100%, that means the HNO3 reacts with the water 100%. Now, I ask my students to write down the chemical equation of here's the acid, here's the water, here's what it's producing. There's the acid, there's the water, here's what it's producing. It's producing hydronium and nitrate. So that's what it's doing. It's doing it 100%. So this is me indicating to whoever's reading this that I get that HNO3 is a strong acid. It's going to ionize 100%. So whatever the initial concentration of this is, the hydronium at equilibrium, or at the end, is going to equal the HNO3 initially. Which means I'm told that value in the question. So it's been told to me. It is 0.080 molar. That's what the concentration of the hydronium is. So see how the math isn't super difficult. I mean, it's if you get that it's a strong acid, that's, I guess, the tricky part is you have to know it's a strong acid. Therefore, it's 100%. Therefore, it's equal to the initial concentration. Then you already know the hydronium. So the pH equals the negative log of the hydronium which we just figured out is 0.080. So then you pull out your calculator and you take the negative log of 0.08 and you write down your answer. Now, I'm going to stop and I'm going to think about sig figs here. For you, those of you who are just kind of jumping in right here and you didn't look at the last one about sig figs, the Sig Fig Rule for a pH, which is what I have sitting on my calculator. Okay, so this answer right there, oh, hang on, there we go. So this answer right there is a pH. This value right here is the concentration. So the concentration uses the Sig Fig rule that you knew back in Chem 11. So how many sig figs does 0.080 have as a concentration? Leading zeros don't count. So the 8 is a sig fig. And so is the trailing 0 on that 8. So this guy has 2 sig figs. So I get 2 sig figs on my pH. Well, the Sig Fig rule for a pH is numbers before the decimal don't count. All digits after the decimal count. So if I have a pH of, and I'll put it up there again, see how it says 1.0969. The 1 doesn't count. It's not a sig fig. So the first sig fig is the 0. The second sig fig is that 9. Okay, so I've got my pH is 1.0969, but I only get 2 sig figs. So I'm going to keep this guy, and then this guy right here has to change. It either stays as a 9 or it goes up. And so I think of it as staying as a 9 or goes up to a 10. Like actually think of it as a 10, which means that to write a 10 in there, this is going to become a 0. So your actual final answer is 1.10. So if you had a 0.080 molar HNO3 solution at 25 degrees, that's its pH. That's what it should be reading, okay, because it goes 100%. So all of the HNO3 turns into hydronium. Now, what if you have a question that asks you, goes the other way, right? So, which is quite typical. It actually has practical application as well. So what if you're sitting in a lab and you've got a solution of hydrochloric acid sitting there and you don't know what concentration it was? So you go, well, how do I solve this? How do I figure out what concentration it is? Well, HCl is a strong acid. So what if I measured the pH of that acid? Will that tell me anything? Could I put in one of those really analytical pH probes, get the pH of that, and can I use that to my advantage? So a scenario, a question that you might see that's related to that is a solution of HCl at 25 degrees has pH equal to 0.025. What is the HCl concentration? Now, some of you might, let me do the question first and then I'll get to the tricky stuff because I don't want to throw you off too much. So here's the theory. HCl is a strong acid, which means it went 100%. It had 100% ionization. So think chronologically here. Way back in the history of this solution, someone took some water, someone took enough HCl to dissolve the HCl into the water to make a certain concentration. That all of the HCl molecules, because it's 100% strong acid, turned into hydronium. So really, if you've got a solution of HCl, you don't have HCl. HCl actually isn't in there. So this was kind of my trick question, actually. What is the concentration? What is the concentration? Well, 0. What was the concentration initially would probably have been a better question. Now, people don't really get too much into the semantics of that. But the HCl turned into hydronium, and it's the hydronium now floating around in the water that provides you this pH that's up here on the board. That concept that strong acids turn into hydronium and really the strong acid isn't there anymore, it's a concept known as the leveling effect of a strong acid, meaning the strongest acid in any solution is actually hydronium because strong acids don't exist anymore once you put them into solution. They've all turned into hydronium. So the biggest cat in the forest is going to be hydronium. It's going to be the strongest thing. It's called the leveling effect, if you happen to come across that. So you have to get the chronology of this. So that hydronium is now being measured by this pH. So if you go back in time, you take the pH, figure out what the hydronium was, and then go back in time to figure out what was the original concentration of the HCl before any of this occurred. That's what we label on the bottle. So when somebody says, you've got a 3 molar hydrochloric acid solution. Well, it's not really hydrochloric acid anymore. It's actually 3 molar hydronium because all the hydrochloric acid turned into hydronium. But the original solution that you made was HCl dissolved into the water. And that's why we label it. We label solutions that way. And this is kind of a weird kind of a concept. But if you get that, you're really starting to get what the idea of a strong acid is. So in this one, I'm going to take the pH and I'm going to use it to get the hydronium and then in my head go, well, that concentration equals the same as the HCl originally because it was a strong acid. So the hydronium concentration for this equals, and again, last video in episode number 4, to get the hydronium from a pH, it's 10 to the power of the negative pH, which, just to save room, I'm going to write it over here, 10 to the power of negative 0.025. So then I pull out my calculator and my glasses so I can actually see it. And I take 10 to the x, which on my calculator is shift negative 0.025. And I get that. I get 0.94406. So this value is 0.9440608 molar. Now that's obviously too many sig figs. So how many sig figs do I actually get? So Sig Fig Rule again, pH. Whatever comes before the decimal doesn't count. Whatever comes after the decimal does count. And this is kind of a weird one because the 0 doesn't count, but everything after does, including that 0 right there. So that pH 0.025 has 3 sig figs on it. A weird concept, but it does. It has 3 sig figs. So this has to be rounded to 3 sig figs, which means I'm going to take 9, the 4, and the 4, and then that 4 stays a 4. So this is 0.944 molar. Now, if you're, you can just kind of jump to the chase and say, well, the HCl concentration had to be the same number. This is 100% strong acid, so all the hydronium equals the HCl. So it's 0.944. If you've been asked to kind of logically provide some evidence or some proof of why that is, then I accept this. Chemical equations tend to work. So I accept HCl in water reacts 100% to form hydronium plus Cl minus. Therefore, the HCl initial equals the hydronium at the end. Therefore, whoops. It's 0.944 molar. So that is you kind of using your chemistry lingo to say, I get that it goes 100%. So the hydronium that got made, which is what I calculated up here, is connected to the HCl in a 1-to-1 ratio because it's 100%. Which, next class, which is what we're going to start doing, next class, we'll get into the weak ones that don't go 100%. And it gets a little bit messier because when it goes at less than 100%, you can't use your old Chem 11 limiting reaction, simple stoichiometry. You have to get into KEQs and things of that nature. So that's where we're actually going to take that Ka table and actually figure out what a Ka is and how to use it. Okay, we'll see you then.